Hurry, step right up. You, sir, and you, madam, step right up. Hurry. Hey, you, at the face. Ride the Cyclone.
This is my Cyclone pinball machine. It was made in 1988 by Williams. I've got the playfield glass off to show you an issue I've been having. We'll start up a game.
Hurry, step right up.
So a normal flipper, when you fire it, it's like that. It's a pretty strong fire of the solenoid. My left one, however, you can see it barely moves. Interestingly, if I push it up first and then push the flipper button in, it's pretty strong. I can't push it down.
Hey, you.
So let's take a look under the playfield and see what the problem is. These are the solenoids for the flippers. When you push the flipper button, you can see the solenoid activates and it pulls this metal plunger into it. The flipper bed is connected through this shaft right here. So when the solenoid fires, it moves the flipper like this. You can see there's some switches here. The power from to the solenoid actually comes in via this large switch here, this normally closed switch. This normally open switch here activates your lane change. So when the flipper fires, it closes this switch. They've got this buffer here because this is a high power switch. Flippers normally work on a 50 to 70 volt range. So this is high voltage on the switch when the flipper is activated. This is low voltage. This is just a 5 volt signal to the CPU to let it know the flipper was closed. So that's why there's this plastic buffer here. If these two things were to make contact, it would blow up a lot of ICs on the CPU board. So the power to the flipper actually comes in via this black cable here, and then runs through this switch. So a good flipper stroke is strong like this. If we were to not allow that switch to make contact, you can see the solenoid's twitching. It's trying to fire. And in fact, if we were to manually activate the solenoid and then hold the button in, it's pretty strong. That's because on modern solenoids, on a modern pinball machine solenoids, there's actually two paths through the solenoid. There's the high power and the low power. The high power activates the strong initial stroke. The low power holds that stroke in. So this is activating the high power side, and this is the low power side. It just holds it in. So you get a really strong initial stroke, and then when you hold the flipper in to catch the ball, there's a lot less power running through the solenoid, so it's a lot less likely to burn up. If this high power side were to stay active very long, the coil gets really hot and it gets burnt. You can actually see on this old original coil, it's kind of burnt. That's because it's gotten so hot over the years. You may notice that this switch here, this normally closed switch, I don't know if you can see it on the film, but it's corroded. As I said earlier, this switch carries 50 to 70 volts. It's high voltage, and that causes those tungsten contacts to pit, and they get some carbon buildup. So, what's happening with my weak flipper, or my failure to fire, is that carbon buildup and this pitting has caused this switch to not conduct well. So all I'm getting is the low power side of the solenoid. Now you can see the flipper's working now. That's because I've gone through and filed off some of that corrosion and buildup. So it's getting a better signal now, but it's still weak compared to how it would be if this switch were clean. So that's the issue. I think we need to replace this switch. And while I'm in there, I'll look at replacing this capacitor, and replacing the coil sleeve, and replacing this spring. That should make the flipper's fire a lot stronger. Another thing you want to look at if your flippers are weak are the leaf switches for the flipper buttons. So it's a simple mechanism. When you push the flipper button on the side of the machine, it makes electrical contact on this switch, which fires the flipper. I don't know if you can see, but there's some carbon buildup on the switch contacts. Now I replaced this switch less than a year ago, so this one's not bad. But on some machines you'll see a lot of buildup there, and that prevents strong flipper action. On these older machines, up until, I think for Williams, up until Getaway in 1992, these flipper switches carried the full voltage of the flippers. So this switch is actually passing 50 to 70 volts. Starting with Getaway, the flippers were CPU controlled, so this was just passing a 5-volt signal. They called that Fliptronics, and on those machines, you won't see any buildup here, so these switches would never have to be replaced. But on the older machines, you definitely need to take a look at the flipper button switches and clean any corrosion, or just replace the switches. Just like on the flippers, you'll also see a capacitor going across the switch contacts. I changed these capacitors and the switches, like I said, less than a year ago, so you shouldn't see any sparks, or at least minimal arcing across this switch because of the clean contacts and because of the capacitor. We'll take a look at this one and see if it's arcing. Nope. So clean contacts and a good capacitor are going to give you strong flipper action. I noticed something else wrong with these mechanisms while I was examining them. You can see on the left flipper there's 2 diodes, one on the high side of the coil and one on the low side. But on the right flipper, I've only got 1 diode, so I'm missing the one on the high side. These diodes are called flyback diodes or snubber diodes. They go across an inductive load to prevent a voltage spike when the flipper releases. So we apply voltage to pull in the solenoid, and then when we release it, that voltage goes back the opposite direction, back to the CPU, and it can be a huge voltage spike. That's eliminated by putting a diode in the reverse direction across the inductive load. So missing this diode on the right flipper is exposing circuitry to a high reverse voltage spike. So we've got to take care of that. So these lane change flippers just carry a low voltage, so we can leave those in there. You can just take a business card, maybe soaked in some alcohol, and rub them between these contacts to clean those off. So we can leave these in the machine. The switches that we need to get out of the machine to work on are these end of stroke switches here. So let's get these flipper mechanisms out. I've got to cut off these wires to free the whole mechanisms from the playfield. I like to leave a little bit of insulation so I can tell which wire was plugged in where. I've also taken pictures of all the mechanisms and the wiring, so that I can be sure I put them back the right way. If you, for instance, if you flip these around, or if you install a diode backwards, you'll fry some circuitry. So you got to take good pictures and make sure that you get stuff back the way it was. Next thing to do is to release the pawl from the flipper bat. That'll allow you to take out these screws and pull the entire mechanism off the playfield. These are two different rebuild kits. This one's really nice because all you have to do is release this one nut. This one you've got to hold this bolt steady and take the nut off. So when I rebuild this flipper, I'll replace this mechanism with one of these. These are a lot nicer. So I've replaced the end of stroke switches on both the left flipper and the right flipper. You can see I'm comparing the end of stroke, the new end of stroke switch, how clean that is compared to the corrosion you see on this one. Unfortunately, I'm going to have to wait to finish the right flipper because this coil seems to have overheated. When you get a rebuild kit, they provide a new coil sleeve. You don't normally need to replace these coils, just the sleeve, because the coil itself isn't a mechanical device, it's just a winding of wire. The only thing that goes wrong with them is, well, the diodes fall off, but that's easy to replace. But more importantly, is sometimes they'll overheat. When that happens, you'll get this browning of the coil wrapper, and you'll also find it difficult to remove the coil sleeve. So this one should look like this. I was trying in vain to get it out, and I ripped off the lip of the sleeve because this sleeve would not come out. So that's a sign that this coil has overheated. When it overheats, it expands, and the inner diameter gets smaller, and that constricts the plunger and doesn't give you a smooth flipper motion. So if the sleeves are difficult to get out, or if the new sleeve is difficult to get in, that's a sign you should replace your coil. When you replace the coil, you want to be careful to use the diode to tell you where to put your new leads. So look at your old coil, and regardless of where the connections physically were on the old coil, look at where they are in relation to the banded and non-banded sides of the diodes, and install your new wires to match the positioning that in relation to the diodes, because some of the coils are wired differently. This is the Cyclone flipper coil. It's the FL11630. It's the most commonly used flipper coil. Sometimes you'll see the FL11629. That's a bit stronger of a coil. It's got a blue wrapper as opposed to this 630's orange wrapper. Flipper coils are very simple. They're just windings of wire around a hole in the middle. This nylon sleeve comes out. Replacing this sleeve is just a maintenance action. The plunger for the flipper goes into the sleeve, into the coil, and they get gummed up, and they get some carbon buildup and just dirt inside of the sleeve. So you take these sleeves out and replace them, and that gives you smoother flipper action. The solenoid, the plunger is attracted into the coil due to the electromagnetic field that the coil produces, and that's produced by current going through these windings of wire. You can see this coil has 3 terminals, and from each terminal you can see a small copper wire going into the windings. And actually, if you look closely on this first terminal, you can see there are 2 wires. There's one above this this piece of paper here that loops around the plastic. There's one above it, and there's one below it. That's because this is what's called a parallel wound coil. So there's actually 2 conductors coiled around the sleeve. Both of them start from this terminal, and one winding is between these 2 terminals, and one winding is between these 2 terminals. One of them is produces a very high power magnetic field, and the other one produces a smaller field. Flipper coils normally have 2 different windings. One of them is used for the initial stroke of the flipper. So that's what moves the flipper from rest to the up position. That's a very high-powered movement. It's a very it uses the strong magnetic field to produce that movement. And then the second winding holds the flipper up in that up position. So once it's moved from rest to up, the second winding holds it there. They do that because the high power winding that produces the initial movement passes a lot of current. And if you were to keep that winding active, it would actually melt the coil. So to prevent that from happening, they use the low power winding to hold the flipper up. So then you can hold the flipper up and cradle the ball for as long as you want to, and it won't hurt the coil. So that's the reason for the 3 terminals. The diodes that go in between the leads are called flyback diodes, and you'll see those on any kind of inductive load. What happens is when the magnetic field is produced, and then when it collapses, when you push the flipper and then let go of the flipper, the field collapses, and when that happens, it sends a very high voltage spike in the reverse direction. So we've got power flowing, for instance, from this terminal to this terminal to produce the field. When we let go of the flipper, you would see, instead of power flowing from here to here, you'd see a very high voltage spike of power flowing from here to here, and that voltage spike can be many times larger than the voltage that was used to produce the field in the first place. And that spike would travel back through the circuitry, the flipper circuitry, and fry components. So to stop that from happening, they put these flyback diodes or snubber diodes reverse biased, so that voltage spike, instead of going back this direction, just travels through the coil like this. So normally the diode is reverse biased, like I said, so power coming in through here can't pass through the diode in this direction. It can only pass in this direction. So it's only the reverse spike that goes through the diode, and that protects the flipper circuitry. This is a replacement coil. It's not an original Williams coil. On some replacement coils, they actually put a schematic on the wrapper that shows you how it's wired and what each of these terminals is meant to be connected to. So you can see there's no schematic on this one. So let's draw one. We'll call this terminal 1 and terminal 2 and terminal 3. So say we've got 1, we've got 2, and we've got 3. So this would be connected to the power source. Let's call it 50 volts DC. And then these two are eventually connected to ground. So as we saw, we've got 2 wires coming in from terminal 1. They loop around the nylon sleeve in the middle, and then exit to terminal 2. And there's another one here that exits to terminal 3. And then we saw we've got reversed bias diodes between them. Like that. So that's why they call it a parallel wound coil. It's because these aren't in series; they're in parallel. So the electromagnetic field of a coil, the strength of that varies based on two different things. The amperage traveling through the coil, and also the number of turns. So current is volts over resistance. So to increase the amount of current traveling through one of these to make it higher power, we need to change the resistance, because the voltage for both of them is consistent at 50 volts. So you can do that in two different ways. Every bit of wire has a little bit of resistance to it. So making the wire longer will introduce more resistance. Also, if we decrease the wire diameter, that adds more resistance. So if we can add more resistance, it will decrease the amount of current. Decreased current produces a weaker field, and it also produces less heat. The way that they increase current on one of these coils is by using a shorter wire length. Now with a shorter wire, they can't make as many turns around the sleeve in the middle. So less turns is a less strong field. And the way they offset that is by making the wire a little bit larger in diameter. So between 1 and 2, that being the short run, this is actually a thicker wire. And that allows it to, by passing more electrons, that allows it to produce a higher power magnetic field. And also because it's a shorter length of wire, it's got a lower resistance, so that again increases the amount of current that it can pass. So this ends up being low resistance, and this coil ends up being high resistance. So you've got a strong field here and a weak field here. So let's see if we can verify that on the actual flipper coil. I'm going to put my meter in resistance mode, and I'll put the positive lead on terminal 1 where power would enter, and I'll put the negative lead on terminal 2. So this should be the high power side of the coil. So we get 4.7 ohms across between terminal 1 and terminal 2. If we measure between terminal 1 and terminal 3, 147.7 ohms. So it's significantly higher resistance. So that's what produces the weak field on the side between terminal 1 and terminal 3, and the strong field between terminal 1 and terminal 2. Because as resistance increases, current decreases. If we look outside the flipper coil and look at the mechanism as a whole, we see that there's power coming in here, 50 volts like we said before. So you've got a conductor coming in here, and then you've got another conductor coming off of terminal 3 that goes to eventually goes to ground. So positive volts here on terminal 1, ground on terminal 3, and there's also a switch. The the end of stroke leaf switch is actually between terminals 2 and 3. So this switch is normally closed. So you can see it has the effect of shorting the high resistance coil. When the flipper is at rest, the high resistance coil is shorted. I should have drawn it closed, normally closed. Once the flipper makes its initial stroke, and it's being held, this switch opens, and then at that point, the high current winding of the coil doesn't have a path to ground. So the only path through the coil is the low resistance. So when the flipper's at rest, this high current side is enabled. When the flipper is up, this high current side is disabled. On parallel wound coils like this, you'll also notice that there's a capacitor across the end of stroke switch. So this is the flipper coil passes 50 volts, and 50 volts is enough to jump the air gap between the contacts on this switch. So it's normally closed, and you hit the flipper button, which actuates the flipper, and the flipper's motion actually opens this switch. And when it opens, you'll get a spark, an arc across these switch contacts. And over time, that arcing will deteriorate the switch contacts. It'll corrode and pit the contacts, and that leads to the problem that we've been having on Cyclone. So to help combat that, we place this capacitor across the switch contacts, so it's in parallel with the switch. So as the switch opens, it creates a voltage differential, because now this side is positive from the input voltage, and this side is less. So there's a differential across this capacitor, and that causes the capacitor to charge. And the capacitor can charge faster than the switch contacts can open. So as the switch is opening, the voltage that would be arcing across the switch contacts is instead charging this capacitor. So putting the capacitor in parallel with the switch prevents arcing across those contacts and prolongs the life of the end of stroke switch. We're ready to install all the replacement parts into the flipper bracket. Your flipper rebuild kit will come with several different components. A new coil stop. The plunger of the flipper mechanism hits the coil stop pretty hard, and sometimes it'll mushroom around the edges, and that'll cause it to get stuck in the flipper coil's nylon sleeve. So they send you a replacement coil stop along with 2 bolts and lock washers to hold the coil stop on. That bolts on right here. It'll come with a new coil sleeve. Now in this case I got a replacement coil, and replacement coils typically come with sleeves, so I'm using the sleeve that came with the coil. But rebuild kits will come with these. It'll come with a new plunger and link and arm. These come assembled, so you won't have to worry about that. And the ones I like are notched right here, so you tighten this side, and you don't need to worry about steadying this side while you're tightening this one because it's locked on. Sometimes you'll get them where they have a screw head here, and then a nut here, and you've got to hold this down while you tighten this. I like these a lot better. It'll come with a new plunger spring. You'll notice that one side is much wider than the other side, so it's important to put them on in the right direction. It'll come with a new capacitor to go across your EOS switch, your end of stroke switch. Now I've already installed this. I did this before I realized I needed a new coil. So you can see I've already got the end of stroke switch mounted to the bracket, and I've got the leads from the capacitor going to each side of the end of stroke switch. It doesn't matter which side goes to which. These capacitors are non-polarized, and both sides of the EOS switch are electrically the same. So you can solder them on either way you want to. Now it does matter which direction your EOS switch goes. Now the flipper rebuild kits sometimes don't come with these, so if you're rebuilding a flipper mechanism and your kit didn't come with an EOS switch, you probably want to go ahead and get one, and go to the trouble of replacing it if it's corroded and pitted like mine was. So this switch, they mount on the inside of the bracket towards the flipper coil, and the large arm of the switch goes on the outside. The flipper mechanism will push against this to open it, so this arm needs to be on the outside. The rebuild kits typically don't come with the flipper bushing. So this is the part that goes through the playfield. So this is the playfield side of the mechanism. This is under the playfield. So this pokes through the playfield, and the flipper bat goes into it like this. So when the flipper rotates, it's rotating within this bushing. So to get smooth action on your flippers, it's important that this bushing is clean. And sometimes they get worn down here, and they get worn down here. In fact, this one is a little bit worn down. Normally I replace these while I've got the flipper mechanism out, just to get it done, but in this case I don't have these on hand, so I'm just going to clean the inside of this one with a little bit of alcohol and a Q-tip. Because it's got some dirt built up inside of it. So I'll just try and scrub that out a little bit. So we're ready to solder the end of stroke switch to the flipper coil. Now, every time I take apart any mechanism, I always take a lot of pictures. So I've got pictures of how this was originally installed. But let's just go by our schematic because we went to the trouble to figure this out. So we decided that the end of stroke switch provides a ground path for the heavy duty winding of the coil, the high current coil. So we know that the side of the coil that has two leads coming out of it for the parallel coils goes to the positive voltage, the 50 volt line, and then the end of stroke switch goes across the other two terminals. So it provides a ground path for terminal 2. So when this switch is closed, the heavy duty coil has a path to ground. When the switch is open, it doesn't. So the only coil that's active is the low current coil. So we know the end of stroke switch needs to go between terminals 2 and 3, the second and third one. Now if we look close, I don't know if we can see it, but the terminal 1 has the two leads, so we know that's positive voltage. And if you look really close, I'm not sure if we can see it here, but terminal 3 is a narrow gauge wire, and terminal 2 has a wide gauge wire. So you can tell that here to here is the high current, here to here is the low current. So we're going to attach these two wires that go to the end of the stroke switch between here and here. So the coil sleeve protrudes a little bit on the end, and the reason for that is to hold it within this circle. So make sure that you've got your sleeve positioned right so the lip is on the side with the terminals. And we'll just slip this in here. I don't want to tighten down the stop to hold the coil in quite yet, because all I want to do at this point is hold the coil steady while I'm working on it. We'll need to take the coil out to get this linkage installed, so we don't want to put it all the way in yet. So let's just finger tighten these. It'll just hold the coil in place. So, terminal 1, 2, 3, we're going to connect the end of stroke switch here. So that will be on the non-banded sides of the diodes. The bands and the diodes are here and here, so we're going to connect here and here. So when I'm doing this, I like to make sure that the wires have a mechanical connection to the terminal, so the solder would hold the wire on once it's dried, but the vibration that the coils experience might cause that solder joint to break. So I like to try to make sure that the wires are kind of holding themselves on, and I do that by trying to insert the wire through the holes in the terminal. Now there's lots of times there's already a solder applied to these terminals. In fact, there always will be solder applied to these terminals when you get them. Sometimes you've got to remove some of that solder to expose the hole. In this case I didn't. It was already exposed. So I've got the end of stroke switch connected between 2 and 3, and now I can go ahead and solder that on. So you can get some solder on your soldering iron if you can kind of tin it and get a little extra blob of solder on there. It helps with the heat transfer because the solder transfers heat really well. So we want to heat the terminal and heat the wire, and then apply the solder to the wire. You'll pick up some, you might pick up some insulation that melted off the end of the wire and some crud from the terminals, so you make sure your tip is clean. So we've got, these wires are secure on pins 2 and 3. lots of people talk about the proper way to install a coil is with these terminals on this end, because this flipper plunger is going to come in this direction and it fires like this. So when the flipper plunger hits this coil stop on this side, it's pretty violent. It hits it pretty hard. So there's a lot of vibration. And there's probably a bit more vibration on this side than there is on this side. So if you can get these solder joints away from that vibration, conventional pinball community wisdom says that those joints will last longer. However, it wasn't installed that way from the factory, at least not from Williams. And the lengths of wire that you've got under the playfield are made assuming that you're going to make your connections on this side, not this side. So I typically just go ahead and install it the way it was at the factory. I haven't had any of these fall off yet. So now we're ready to install the flipper plunger linkage. It's easiest if you remove the coil and pull it back a little bit so you can scoop this in there. One point before we do that, let's take a look at this flipper bushing that we talked about before. It's important if you're replacing this that you don't try to do it from under the playfield. Like I said before, this is the under playfield side. This is the playfield side, so you can't normally see this when it's installed. So you may be tempted just to, if you want to replace this, just unscrew these and pull this bushing out, and that would allow you to do it without removing this entire mechanism, but you can't do that. Because they're held on via these nuts. And if you try to just remove the screws from this side, you're going to strip the screw head. And you're going to lose these nuts, because they'll fall somewhere in the playfield. So if you want to replace this bushing, you've got to take the whole mechanism out. You want to use a screwdriver to steady the bolt head, and then use a nut driver to remove these nuts. Sometimes I see people use Loctite on the nuts to hold them down. I haven't found that necessary. You might notice that on this particular flipper bracket, on this bushing install, these are flathead screws that would imply, if you saw that, that you can't put a lot of torque on these. So it might remind you to make sure to use a nut driver instead. Lots of times you'll see these are Phillips heads. So I've often forgotten that I have to use a nut driver instead, and I'll try to unscrew it with a Phillips head screwdriver, and it just strips it. And it's a pain in the ass to get off. So make sure if you're replacing these bushings, I'm not, but make sure if you're replacing the bushings that you use a nut driver. So let's pull the coil stop off. Make sure not to lose the lock washer. And we will scoot this coil back a little bit and install the plunger and linkage. You have to be careful to install this in the right direction. So when the flipper fires, it pulls the plunger in. That moves this arm outward like this, and that outward movement is what opens the end of stroke switch. So you have to make sure that this arm is hitting the end of stroke switch when the plunger is pulled into the coil. So you don't want to install it this way, you want to install it this way. And I almost forgot, you need to install the spring, the plunger spring. So the small end goes on top, so it meshes with this tapered edge of the linkage. The big end goes on the bottom, so that it fits into the four arms around the hole right here. So we'll just slide that into the coil a little bit. Then we can get the coil back on. Like that. And now we can tighten this down for real. Unlike the flipper bushings, the holes in the flipper bracket for these coil stops are threaded, so these just go right into the bracket, and you don't need any nuts to hold them on. Before I tighten them down all the way, I need to make sure that the coil is steady and is tight into the mechanism. So we just want to apply some pressure, really pinch the coil in between these two brackets. If your coil is loose, a lot of the movement of the plunger is going to be wasted on moving the coil instead of the plunger. So we don't want that. So the coil has to be really tight. That'll give you the strongest flipper action. And you really want to tighten these down because, like I said before, the coil hitting the coil stop is pretty violent. You don't want those to come loose and have your coil just fall out. Or you don't want it to come loose and then have a weak flipper stroke. Alright, that's pretty tight. So now our coil doesn't move a lot. It's pretty tight. It's not going to go back and forth. Okay, so, and we can see the flipper shaft is going to come in through the bushing and go through this hole. So when the coil fires, it's going to turn and it's going to push that arm into the end of stroke switch. Like that. Man, I just caught myself. I always forget this. You don't want to tighten these down yet because there are bolts that have to go through this switch stack to the lane change side of the switch stack over here, and we can't install those yet because they're still attached to the playfield. And it's really hard to hold those bolts down when you're trying to install the rest of the switch stack when this coil is installed. So you really don't want to tighten this coil down yet until you're ready to reassemble this switch stack. So once we get that in, once we get the mechanism mounted on the playfield, we'll have to loosen these and move the coil so we can get the access to the switch stack. So now we're ready to reinstall the bracket into the playfield. So there are 8 bolts that hold the flipper mechanism, the flipper bracket, to the playfield. You don't want to tighten them. You don't want to overly tighten them because they're screwing directly into the wood. And you might just damage the wood and pull the threads out of the wood if you tighten too much. That's why there's 8 of them. So just snug on all 8 is enough to hold the mechanism on. So now I've got the mechanism secured on the playfield. The next thing to do is to wire up this switch stack. This is the lane switch side of the switch stack. It goes on the outside of this arm, while the end of stroke switch goes on the inside. As I said before, you probably want to temporarily remove this coil to give you better access to the nuts, to these nuts, which are going to go on the inside of the switch stack, close to the coil. If you don't do that, it's really hard to get in there and keep those nuts steady. while you're screwing the screws through the switch stack. So let's just take this stop off. So two things you don't want to forget to do is reinstall this fish paper. This just adds a little bit of insulation to the end of stroke switch. So it goes in between the end of stroke switch and the bracket, and also in between the end of stroke switch and this plastic buffer. That helps insulate the high voltage of the end of stroke switch from the low voltage of the lane change switch. So don't forget to reinstall that because it probably fell off when you were taking the mechanism apart. And then this one of these metal plates goes on the far outside of the switch stack and the far inside of the switch stack. I often forget to reinstall this. And then I gotta redo it once I think I'm done. So we've got the switch stack reinstalled. Now let's install the linkage and the coil and the coil stop. So it's pretty sturdy in there now. So double check to make sure that this hole in the linkage will line up with the hole in the flipper bushing, and that when extended the arm gets close to the end of the stroke switch. We can come back later and bend the end of stroke switch if we need to, and bend the lane change switch if we need to. But you just need to make sure that this is installed in the right orientation. So we're ready now to reconnect the power and return lines to the flipper coil. Now is a really good time to check the pictures that you took before you disassemble these mechanisms, to make sure you know which one of these is power and which one of these is return. The power line is going to go on the terminal that has two wires going to it. So that's this one in our case. And the return line is going to go to the terminal that has a thin wire going to it. The power wire should go on the banded side of the diode, and the return wire should go on the non-banded side of the diode. I like to strip the insulation off of these and any of the previously exposed copper to get a really good new clean connection. So I'll connect my power wire to the first terminal on the banded side of the diodes. And then we'll go back and do the return side. This is the part that makes me wish I had 3 hands, because the return side is connected to, the terminal is connected to 2 different wires. And we've already covered the hole on the terminal with 1 wire. So it's hard to get the second wire to stick. So next we need to reinstall the flipper bat. If you've got the machine apart this much already, and you've already had the mechanism out, and maybe you've replaced the bushing, you might consider just replacing the flipper bat as well. And also the rubber that goes around the bat. I've had the shafts break at the junction between the shaft and the bat. And that makes for a really weak flipper stroke. And they just get dirty and cruddy. So you might want to replace it. The flipper bat goes through the bushing here, like that, and then this arm goes around it. Like that, and then it moves like this, yeah, and turns the flipper bat. When you're lining up the flipper bat on the playfield, you'll see 2 really small holes right behind the bat, close to the player. Those are just big enough to insert a toothpick into, and they're meant to help you line up the flippers. So I'll stick this toothpick in one of those holes and then push the flipper bat against it, and that lines up the flipper at its resting point. And then you make sure that your plunger is completely at rest against this stop. And then you're ready to tighten this bolt against the flipper shaft. It's got to be, the pawl has to be really tight against the shaft, so you really want to torque this guy down. So I'm holding the bat against the toothpick. You want to leave a little bit of clearance between, on the playfield side, between the top of the bushing and the flipper. And you also want to leave a little bit of clearance between, under the playfield, between the bottom of the bushing and the pawl. Sometimes you'll see a gap tool that you can insert here and here between the above and below the bushing. That ensures about, was it 1/8 of an inch? So there's an official gap tool for that. Some people just take a credit card and cut a notch. Right now I'm just going to do it by feel. So make sure the toothpick is perpendicular with the playfield. Make sure you've got an 1/8 of an inch gap above the bushing and below the bushing. Make sure your linkage is at rest. Your flipper is at rest against the toothpick, and then tighten the crap out of this bolt. So next thing you want to do now that you've got your flipper installed is check the alignment of the switches. You want to make sure that when the flipper is at rest like this, at the end of stroke switch contacts are making really solid contact with each other. Because a lot of voltage has to pass through those contacts for the high side of the flipper to work. Then you want to make, and also you want to make sure when the flipper is at rest that these lane switch contacts are not making contact. And in this case, they are. So we have to bend these out so that when it's at rest, it's not making contact. And to do that, you use a leaf switch tool. You can get different kinds from different resellers. So I like to have these two because this end of the tool is different. So it allows me to get into tighter places. So I'll use this to bend the contacts on the lane change switch, so that it's not making contact when the flipper is at rest. And you want to bend it just enough to get it so it's not making contact, and then enough so that when the flipper actuates, it is making contact. So what you want to see when the flipper is up is about a 1/16 or an 1/8 of an inch gap between the end of stroke switch contacts and the solid contact here on the lane change switch. And that's about what I've got. So at maximum stroke, I've got about a 1/16 of an inch gap in the contacts for the EOS switch and pretty solid contact here. You also want to see that the top leaf of the EOS switch, when I open it, I want to see it kind of move down a little bit. That tells me that when these contacts are together, they've got really solid contact because they're pushing against each other. And when that pressure is relieved, the top one moves down a little bit. So I might actually want to increase that just a tiny bit. Normally normally everything kind of lines up on the EOS switch side, like they're manufactured, just the way they need to be. So I think we're pretty good here. Next thing you want to check is that there's no contact made anywhere where there shouldn't be contact. So I look at all my solder connections to make sure they're solid. Make sure those uninsulated connections are not touching anything they shouldn't be touching. So I kind of tug on all the wires on both sides of the switch stack. Especially on my flipper connections. Then double check to make sure that the power side is on the banded side of the diode. The return side is on the unbanded side of the diode. And then I've got my EOS switch installed over the weak side of the coil. Make sure that the spring, the large end of the spring, is sitting within the 4 little arms that hold it. Check your gap, and then just do a double check on everything. think at this point we're ready to fire it up and see if it works. So cross your fingers, hit the switch. It'll probably do a ball search because I took the ball out when I lifted the playfield. Let's go ahead and put this lamp back in. And we'll put it in diagnostic mode. And now the flipper should work, so. And it does. So what we're looking for here is when I'm holding the flipper in, I don't want to see any arcing across those switch contacts. A little bit of spark is okay. A lot of spark maybe means the capacitor isn't connected right. And I also want to, if I go into lane or switch test mode, I want to make sure that when the flipper is fully extended, that I see this lane change switch being activated. So switch edge, and if I move the flipper myself, you can hear that the switch is being activated. It's probably hard to hear on camera, but I can hear it there too. So I think everything's working right. I think we're ready to lower the playfield and give it a try. So with the playfield back down, you can see that now we've got a really strong flipper stroke on each of them. Looks like we're back in business.
Ride the Cyclone! Hurry, hurry! Step right up! Hurry, hurry! Hey, you!